Hello everyone, thank you for joining. My name is Tobias Duin. I am a machine learning engineer at Soundtrack Your Brand, and today I'm going to talk about deep learning for music recommendation. Soundtrack Your Brand is a Stockholm-based company that provides background music for businesses. So think restaurants, bars, hotels, spas, anyone that wants to play music for an audience and really cares about the theme of that music. They can go into our app, they select the style that they want, and then use our catalog of 50 million songs to create a soundtrack that never gets repetitive and yet always fits the theme. So a quick example, here on the left we have a soundtrack that we would describe as human and inclusive.
To wake up with you will be everything I need.
And on the right we have a soundtrack that we would describe as expressive and provocative. So what this means from a machine learning perspective is that we have to figure out how to separate these two feelings and these two themes. And that means that the sound signal is absolutely everything. That also means that mistakes are quite costly. Putting a rock song into a lounge soundtrack is really bad. And yes, it has happened once in the past, but right now we're pretty good at not doing that. But what it also means is that it's a lot of deep learning on top of raw audio. And with most deep learning, you can toss your data into a model and it will get you somewhere. But if you want to be good at it, it helps to know what is really going on inside those models and what are the types of patterns that these models are supposed to learn. And that's what I like to talk about today. Like, what are the patterns that we are expecting to find in music? And when answering that question, we also find that there's a big overlap between the physics of sound on one hand and music theory on the other hand. So where to start? Well, with machine learning, I usually find it helpful to focus on how we as humans process a signal and then try to gain inspiration from that. So what I like to try and answer is, for example, how can it be that our ear can distinguish between two different instruments? So let's begin with sound. Sound is a pressure wave that travels through the air, caused by a vibrating object at the source, and then at the very end we have our ear trying to make sense of those vibrations. And normally when you display sound, you put the air pressure on the y-axis and then time goes on the x-axis. Right now you're looking at a single whistling tone. And when our ear tries to interpret this signal, then the frequency becomes the pitch of the tone, or the tone height, and the amplitude becomes the volume of the tone. Well, that's a story for one frequency at least. But most tones are very complex structures of frequencies. Here, for example, we're looking at a piano note. It's still a single note, but there's a lot of frequencies in there. And as you can see right now, it already becomes quite hard to interpret. An easier way of displaying this is a so-called spectrogram. There is no new information here, it's exactly the same, it's just displayed in a different way. Time still goes on the x-axis, but the y-axis now is the frequency. And there's a third dimension, which is color, which resembles the amplitude. And this is our piano note in a spectrogram. And as you can see, this piano note consists of a whole range of frequencies. And all these frequencies, they seem to be in a pretty structured pattern. So to answer what this pattern is, I'll introduce a bit of semantics. The lowest frequency is called the fundamental, and all the frequencies on top are called the harmonics or the overtones. in music language. And these patterns, they follow very strict rules. So the first rule is that the fundamental is always the lowest. The fundamental is always the loudest. The second rule is that all the harmonics are multiplications of the fundamental. And the third rule is that all the tones start at a similar time. And the fundamental gets interpreted by our ear as the pitch of the tone. And then the harmonics, they together they decide the color of the tone, or the timbre in music. And the funny thing is that if you mess with any of these rules, then this tone will fall apart and our ear will start to hear two notes instead of one. So if we take, for example, the fundamental and we decrease it in volume, making it not the loudest anymore, then all of a sudden our ear will hear two different notes. The fundamental will turn into a very thin note with just one frequency, and all the overtones together will form a very rich note, but then starting a lot higher. So the pitch of that rich tone will be higher. We can change the offset of a frequency. That will also turn this signal into two separate notes. And we can also mess with the rule of multiplication. So if we take a couple of harmonics and we move them up or down so that they are no longer multiplications of the fundamental, then this will also be interpreted as two different tones. What is free to change, however, are the volumes of all the harmonics. And that is exactly what describes the color or the timbre of a tone. So the difference between a piano or a guitar or a whistle is the volume of all the individual harmonics. In general, you can say that the more and the louder the harmonics, the richer the tone. As you remember the whistle from earlier, it was just one frequency. And now we're looking at a piano with a whole range of frequencies, and a piano is usually perceived as a very rich sound. So why do these rules exist? Why has our ear learned that to interpret it in this way? Well, that has everything to do with the way that sound is created. All objects can absorb energy by vibrating, but they can only do so in a very limited amount of ways. So every object absorbs energy by turning it into vibration, but the frequencies of it which it can vibrate are completely fixed, and they are completely dependent on the size and the stiffness of that object. So if we take, for example, a guitar string, and we hit that string, then it will can only absorb energy by turning it into a vibration frequency that fits exactly in the length of that string. But it can also fit exactly twice that frequency in the length of the string. And it can also fit exactly 3 times that frequency in the length of the string. And interestingly enough, a guitar string can vibrate at all these frequencies at the same time. However, the lower the frequency, the higher its capacity to absorb and send out energy. So now that we know the rules, we can visually separate a whistle from a piano tone quite easily, actually. So even if they're played at the same time on the right, for example. So this is no problem for our eye, and this is no problem for our ear either. But let's take a slightly harder one. Here we have a guitar note next to a piano note. They're both rich sounds with a lot of overtones, but we can still recognize the difference. So with the third example here on the right, They play at the same time. And as you can see, it gets harder for our ear, it gets harder for our eye, but we can still do it. And now comes the hardest one. Like here is still the guitar and the piano, but on the example on the right, they play at exactly the same time. And now you can see, because the harmonics completely overlap, there's almost no way of telling the difference. And this is the case for our eye as well as our ears. That was pretty much one tone, and that is because there is no more information to go on. Our ear doesn't get any more than that. So the second one just becomes like it's a tone of its own, and when you think about it, that makes perfect sense, because if you think about a piano tone is produced by little hammers, but one hammer hits sometimes 3 strings at the same time. But they start at the same time. They are all tuned to the same tone, so they produce exactly the same overtones. And there's just no way for our ear to tell that apart. So they just become one very loud, very rich tone. When we take these harmonics and we project them onto a piano, then there's also a lot of interesting things to notice. The first thing one might notice, I don't know if any one of you play piano, but the ones that do will start to recognize a very basic chord here. And chords are collections of tones that are supposed to sound very harmonious, or they belong together. And right now we're just looking at C major, which is a very basic chord in music theory. So up until the harmonic number 6, they belong exactly to that chord. And even the 7 and the 9, which are not exactly in there, they're still commonly used extensions to that chord. Another thing you might notice is the scale. Keep in mind the frequencies, or the frequencies of the harmonics. They are at a linear scale, because everything is a multiplication of the first one. But a piano is also a linear scale, because a piano is supposed to resemble what our ear perceives as linear, meaning that all the distances in between every note is perceived as a similar distance. Yet when we map them together, we get a sort of logarithmic scale, which is quite interesting, to say the least. And the reason for this is purely biological. All of our, or most of our senses work in a logarithmic way, whether you talk about hearing, whether you talk about vision, or whether you talk about our haptic senses, our touch senses. And a logarithmic scale is just nature's way of dealing with a very large range of input information, combined with the fact that not all parts of that range are equally interesting to us. So take sound, for example. Our human ear can hear sounds ranging from 20 hertz to 20,000 hertz, which is quite a big range. But human speech only happens in between 100 and 1,000 hertz, so that's a fraction. Now, the area where the human speech is extremely important for us to hear all the minor details and frequencies, because it would help us to understand if someone is talking to us and that person is angry, or that person is happy. This is vital information to our survival. Yet if we think about 20,000 hertz, there might be a mosquito that we can identify. Now, it's very important for us to know that there's a mosquito, but we don't really need to know what mood it is, what mood it's in. Similar with light, when it's really dark, it becomes extremely important for us to understand the subtle differences in texture. But when we're staring directly in the sun, we don't really need to understand what the surface looks like. There's even more. The basics of music theory is that people sat down and by listening they organized all the intervals, ranking from very harmonious, so very pleasant, to a very unpleasant or dissonant. And if we look at the most harmonious interval that people had found, then it turns out that that's also the first harmonic for some reason. And we can understand why that is, actually. We can understand why that is when we start to plot these two tones at the same time and then take all their overtones into account. So this interval is called an octave, from 1 to 2. And it's so basic that we didn't even bother to give the notes different names. Note number 1 is called a C, and note number 2 is called a C. We sometimes refer to it as a higher C. But that's how similar they sound to us. And here you look at all the overnotes of both the individual notes, and now you can see that there are a lot of overlapping harmonics here. And it turned out that when people sat down in the early medieval times and tried to organize all these notes just by hearing what sounded pleasant and what sounded unpleasant, they figured out an exact order in which intervals have the most overlapping harmonics. Here we're looking at the second most pleasant interval, which has the second most overlapping harmonics. Here we're looking at the third most pleasant interval, which has the third most overlapping harmonics. And this is quite fascinating if you realize that there's thousands of years in between the creation of this scale and the understanding of the physics behind it. At the very other end of the scale, we have the very dissonant or the very unpleasant intervals. And one of the most unpleasant interval is the interval that goes from the C to the F sharp, which is called an augmented fourth. And it makes sense that it's unpleasant, because when you look at the harmonics, you can see that first of all, they are all misses, and some of them are even very near misses, which make it even more painful. And this interval was considered so ugly that it was thought to be related to the devil, and it was also referred to as the devil's fourth. And there were times that this was forbidden to play. When you put this interval into a composition, you would get punished for it. So those are kind of the patterns that we could possibly find in music. But how would that work in practice? What does that mean for us when we start to train models on top of this? Well, there is a very popular technique which is called the convolutional neural network, which is an idea that became very popular in image recognition. And convolutional neural networks try to reduce the number of connections between neurons by making use of the fact that information that is related to each other often appears in close proximity to each other, which is of course extremely true when you talk about images. So the way it does that is that it uses this, it divides your picture up into like tiny little images or subspaces, and then it first summarizes each subspace before it can link the information from that subspace to a other subspace. And these convolutions happen several times in a model, making sure that areas that are very far away from each other can also only be linked to each other very late in the model architecture. And in image recognition, this is a great way of grouping relevant information together and drastically reducing the model size and drastically reducing the amount of data needed. But however, the small windows that are common in image recognition are not always optimal for music, because we've just learned that the harmonics can range over the entire y-axis and are separated by factors rather than adjacency. And the x-axis also behaves slightly more like a picture, but it also needs a bit more special treatment, because I haven't talked much about rhythm yet, but the smallest unit of repetition, that's a bar in musical terms, and that's typically around 1 or 2 seconds. So that's quite a larger window than you would use in image recognition. Another popular technique that is used is to project this image onto the melodic scale. And the melodic scale has nothing to do with math. Instead, it resembles how our ear perceives intervals. And it's sort of logarithmic, so it boosts all the distances in the lower frequencies, but it reduces the distances in the high frequencies. But it's not exactly logarithmic. It's a bit more messy than that, a bit more random. But the very big upside of using this scale is that intervals that sound similar to our ear all of a sudden also get similar intervals on the y-axis. So this makes this scale extremely useful for detecting melodies. It makes it less useful for finding harmonics, because all of a sudden you have to, the model has to unlearn the melodic scale by itself to figure out the easy to find multiplications that harmonics are consist of. So these were some of the nuts and bolts of how the music data itself is put together and the type of patterns that are in there. And to finish up, I want to talk a little bit about some high-level points. The first point that I already talked about is the window size and scale. Like, if you use convolutional neural networks, then mind the window size. Maybe use a very large window size, or maybe use more temporal networks that use a window size that is more distributed, and also mind the scale that you use. Melodic is great for melodies, but maybe less great for finding harmonics. Next point to remember is that audio is not exactly the same as music. Music is a subset of audio, but there's a lot more patterns in there. It's a lot more structured, and these structures can be utilized. On the other hand, audio processing is a more mature field, especially speech. So there's more data, there's more software to be found. But the techniques that work well for general purpose audio processing might be designed in a way that they can't really utilize the extra structure that can be found in music. And the last point I'd like to talk about is how to deal with labeled data. Data size is an issue in music recommendation. The biggest open source labeled data set has around 1 million songs. And this sounds reasonable, but the labels are of a questionable quality. You can use human annotators to build up your own high quality training data, but this can take a very long time, especially when you want to use it for deep learning. And even if you get such a useful set, then you still have to divide it about through a huge number of genres and styles. Like, some genres are so niche that they only have a couple of hundred songs in the entire world. So to mitigate this problem, It's advisable to not waste your high quality labeled data on trying to learn the very low level patterns. You're better off using unlabeled or badly labeled data in the beginning and saving your good labels for very late in the training process. You can either do that by training the same model but then use different batches of data at different stages, or you just use different models entirely that you chain together by using embeddings, but still save the good stuff for last. And that was it, really. Thank you very much for listening. I hope I've been able to enthuse some of you for a music recommendation. And if you have any questions, then please reach out to me.